Okay, we don't know this limit is A or what is it, but this suggests that we have R equal 1 here. So this is the rate of convergence in this sense is 1 for the Picard iteration associated to Banach contractions. And also this number, lambda, has a significance, is termed asymptotic error of the method. If R is 1, as I mentioned, this is linear convergence, and if R is 2, we have quadratic order of convergence, and in case we have R between 1 and 2, we say that the convergence is superlinear. And just to show you the case of this method, Newton method is known for having the rate of convergence 2 under appropriate assumptions on F. So it is necessary that F, in this equation, we are solving the equation Fx equals 0. We have seen this is equivalent to x. This is the fixed point problem equivalent to this one. And this t, this our t. So for this case, when f is twice continuously differentiable, then the order of convergence is known to be R to be 2. It's not it's nice proof of this result. What does it mean from a numerical point of view? Because we are discussing today, we are discussing the numerical aspects. This means that the number of exact digits we obtain at each iteration doubles all the time. So let's say at the first iteration we have 1 exact digit, to the second iteration we'll get 2 exact digits, to the third we'll have 3 exact digits, and so on. No, sorry, this is 4. 1 is doubling. So this means that the method is of rate of convergence 2, so quadratic convergence. There are a lot of methods in this family. We have in Romania a strong school on numerical analysis, which is 100 years old, and there are many researchers here. This is another method, Halley method. It assumes that f is 3 times continuously differentiable, and then the rate of convergence in the sense of this concept will be 3, and so on. Now, people are interested to get a big rate of convergence, but all the time, to get a higher rate of convergence, we need stronger assumption on the equation, on the function or on the operator, because all this theory, I'm speaking here on real line, but all this theory is done in Banach spaces. So functional equations in Banach spaces, all this theory about Newton method is translated into Banach spaces setting by Kantorovich almost 100 years ago, less than 100 years ago. So in that paper that I mentioned in another talk, I succeeded to get rate of convergence 1 if f is only continuously differentiable. So you can see rate of convergence 1 corresponds to f is first order continuously differentiable, r is 2 times continuously differentiable, r is 3 times. And it is expected as we increase the order of the continuous differentiability, we'll get a higher order of convergence. In some context, and I stress on this, f is even not continuous. So that all these methods do not work. And I mention here this problem approached by this mathematician who discovered the demi-contractive mappings. This was the reason he was led to demi-contractive mappings, because his operator f was not even continuous. So he needed some theory for non-continuous functions or mappings for such an equation. And this was the source of defining these demi-contractive mappings. Well, now let's consider some remarks. In the first concept of order of convergence, if you remember, we had involved two sequences. So n and alpha n. And we say that this is a relative rate of convergence. Why relative? Because it relates to the convergence of this alpha n. The second concept, this one, if I change a little bit, I'll have it here. And here is R. And this order of convergence involves only the sequence, xn, only one. So we say that this is an absolute rate of convergence, an absolute concept of rate of convergence. So we have these two types of rate of convergence. Now, what I want to show you at the end of this talk, first part of my talk, is that we can combine these two concepts. How? We have this rate of convergence number one. I wrote here. If we can compute for alpha n the second concept of rate of convergence, let's say R, so what does it mean? We have for alpha n a limit of alpha n, it's actually, in our case, a sequence of positive numbers. So n plus 1. And its limit, we know it is 0. If we have such a result, then what does it mean? Alpha n has rate of convergence R, and we have this estimate, and how we read this? We read this as the sequence xn converges to x bar at a rate of convergence at least R. So this is different of the previous rate of convergence number one. What about having such kind of rate of convergences? We need we have an iterative scheme. I don't say what kind. We have this sequence. In many instances, you have seen, I gave a rate of convergence for Banach contractions. We can get rate of convergence or error estimates for most contraction type mappings, even for almost contractions. But so we have analytical order of convergence or error estimate, sometimes only error estimate. If we have there this, it's all right if we can establish such an analytical. What does it mean analytical? We have a formula. We have this for Banach. This distance is less than a over 1 minus a. Distance of x0. This is an, I guess. Then, because this is the sequence alpha n which converges to 0. Then we are done, but in practice we cannot obtain such an estimate for the great majority of the fixed point iterative schemes. We cannot get an estimate of the type 2 either. Or this happens sometimes we have an error estimate of order 2, but is not relevant. And I want to show you this concretely here. This is the simplest example we can have to clear this problem. You can see these sequences, AN and BN. Which is AN? Is 1 over 2, let's start by 2 to 0. Then it's 1 over 2, 1 over 4, 1 over 8, so on over 2 to the power n. And Bn is 1, is 1 over 2, is 1 over 3. Which converges faster? Which one? It's clear, this one converges faster because we approach 0 faster than this one. Look, we now compute this estimate, the order of convergence, and the computation are here. For AN, we have this computation. For BN, we have this computation. And what does it mean? Both sequences have rate of convergence in the sense of this concept 2 are equal 1. But they exhibit different speed of convergence. This is clear for any child that this will go more rapidly to 0 than this one, which goes slower. What does it mean? It means that this order of convergence is not useful. We cannot compare these simple sequences by this order of convergence number 2. We cannot compare. Our order of convergence is useful, as I mentioned, this one is useful for Newton type methods because there we can have analytical error estimates, but here it is simply not useful. So we are led to another concept of rate of convergence. If I have time now, we'll stop here for a break. Let's see, it's 11, yes? 15 minutes break, and then I'll continue, okay?
Thank you so much, sir. Such a fantastic talk given by you. And you have talked about the iterative methods. And I can see that you have done lots of research work in your career. And we also want to do like this. But I'm trying to learn such things because we have never done iterative methods before this. And thank you so much once again, sir. And this is the time for a tea break. If you are any questions, so you are, if you have any questions, so you can speak with the expert. Okay, after the tea break. Thank you so much, sir.